All right, let's check out some of these homework problems. And we got a chandelier just hanging there. So there it is. And we got some ropes, so some tension, angle 1, angle 2. And we also have tension 2 and tension 1. I know they call it a cable there, but ultimately we're going to be solving for tension. So I'm just going to call that tension right off the bat. And there's our picture. And next is a free body diagram. The dot just represents kind of the connection point here. And the object has mass, so there's always gravity down. And I'm drawing the vectors out. So here's the force of gravity. There's a force of tension going off this way, tension 2. And there's another force of tension going off this way, tension 1. So there's weight, there's a tension, there's no normal force because there's no surface contact, and there's no force applied. So the four things we're looking for: no force applied here is no person pushing or pulling on it. So here is our free body diagram. We'll put a coordinate system down right there and start figuring things out. Now we do need to get these angles. We do need these angles on our picture here. So just looking at this here, if we do this angle from trig, so I'm just trying to draw kind of a trig thing that maybe you remember, maybe you don't, but this angle here is going to end up being the same angle that's right here. So from trig, when you have a line, split it across, that angle is the one that's right here. So looking at my picture, it's the angle that's right here. This angle also is the one that's right here. So whatever way you know from trig on how to get, oops, that's actually theta 2, sorry. That's theta 2, theta 2 goes here. Whatever you know from trig to get your angle onto your coordinate system, you definitely need to get your angle there. If you look at this, let me try to draw a clear picture of this in case you're not quite seeing it. So let me look at angle 1, and I'm just going to draw this as a rectangle. So here it is. Here's the angle they're giving us. They're giving us that angle right there. And that means it's also that angle right there. So that's trig. Here's where the right angles are. And those angles are equal. And so right over here then is theta 1. So my picture got a little bit messy there. Maybe ignore this bottom line I drew there. But here's where the angles will go. And again, if you kind of draw a rectangle right here, this is the picture I try to draw over here. So you can see that these angles are the same and how I get the angle to be right here. So here's where we're going to start summing our forces together in the x and y direction. And see if I can get a red pen here. So we're looking for the x direction. So I'm just going to start with this left one, T1. Here is the x direction. It's this component right here. That's the x component of tension 1. It's the adjacent leg of the triangle. So what gets us adjacent is cosine. Cosine of the angle that we're given is, they're calling it theta 1. And that equals adjacent, so that's the x component we're looking for, over the hypotenuse, which is just overall the tension, the magnitude of the force there. And so we can solve for the x component by just multiplying both sides by T1, also pointed into the negative direction. So we would get negative T1 cosine theta 1. That is the red line here. That is the x component. We also want the x component for y, which is this line right here. There is the x component for T2. Again, the adjacent leg. We'll get adjacent through cosine. This time we have theta 2 though. And it's pointed in the positive direction. So that would be positive theta 2. And I didn't quite leave myself enough space on the paper there, but the chandelier isn't moving. The chandelier's not moving left or right. So when we set this equal to MA, well, A must be 0 because it's not moving left or right. So these two forces equal each other, and that's how the chandelier here is just hanging without moving, because these forces are balancing out. So these two equal each other. Ultimately, this equation equals 0. Looking at the y direction, and I'm actually going to come down here lower just to make sure I give myself enough space here. I'm going to sum the forces in the y direction down here. So let's look. We'll start with T1 again. The y component is this one right here going up. That's the y component of tension 1. That's the opposite leg, which we can get with sine. It's going in the positive direction. So that's T1 sine theta 1 is that component. For T2, here is the positive leg in the T2 direction. It's going up. So again, up means positive. Sine is how we'll get that leg. And again, that's from theta 2. So here is this component. Here is this component. That takes care of those two components. And the last one then is the weight down. And just look at the math for a quick moment. These two arrows going up. So here's this arrow, the math for that arrow. Here's the math for this arrow. And these two things have to support the weight. These two up arrows have to support the weight going down. That's what the math here says. This component up plus this component up has to equal the weight going down because this isn't moving. So we sum the forces, this equals 0. And so we can see adding these together has to equal mg. So we have, I'm going to write on a new piece of paper here. So we have these two equations. We have this equation here and we have this equation here. And I'm just going to rewrite this so it's clear. So we've got this equation from the first summing of forces, and that equals 0. We have the second equation, again from summing the forces. And since it's not moving, this also equals 0. So those are our two equations there. And it wants us to solve for T1 without having a T2 in there. So it says, find an expression for T1 that doesn't have T2 in it. So we just have to solve one of these for T2 and plug it in here to get rid of T2. And I'm just going to do that from the top because that would be just mathematically the easier thing to do here. So I'm just going to, with the top equation, move this chunk to the right, make it positive. And then I'm going to divide by cosine so that I have a solution for T2. And now that I have my solution for T2, I'm going to take it and plug it into that. So here you go. I'm going to write, whoops, where's my finger? There it is. I'm going to write that T1 sine theta 1 and then plus, but plus T2 where T2 equals this. So T2 equals this. And then minus mg equals 0. So there we go. Here's my new equation. I eliminated T2. And now they want us to solve for T1. And so we can do that by factoring. We'll factor out the T1 here. And I'm just going to move this minus mg to the right side to make it positive. And there is our answer. T1 is mg divided by this parentheses. So I didn't leave myself a lot of space here, but T1 is mg divided by this parentheses. And that's our answer. And I'm not going to type it in, so I'm just going to request the answer. I'm just thinking really fast if there's any math shortcuts they might make with this. No, this looks like exactly how they'll have the answer, what I've written right here. That's my prediction. Let's see what they say. And well, oof. So they did do a trig identity here, and that's a little bit unfortunate. Let me just say this, I guess, really fast. Our answers are the same, but let me just say this really quick. That here's my answer right here. there's no M1 there, just mg over sine theta 1 plus cosine theta 1 over cosine theta 2. So what they ended up doing here is they multiply the top and bottom by cosine theta 2. A perfectly fine math maneuver, nothing wrong with that. So when you do that, you get mg cosine theta 2 in the numerator. Cosine theta, if you bring it along the denominator, it'll cancel this one out, but it will apply to this one over here. And you'll get this relationship. And then this relationship here is a trig identity. That's a trig identity then, where they're getting then how that sine equals theta 1 plus theta 2. But that's how they ended up getting their form, how the cosine gets into the numerator, how the denominator changes completely to, to a completely different trig function. But if you would have put this answer in, I'm confident that it accepts that. I'm confident it accepts that. Knowing trig identities is not required for the course, so they're just being fancy there with the answer. Don't let that scare you. I guess is what I'm overall trying to say. Don't let it scare you. This answer absolutely would have been accepted. Absolutely. Trig identities are not required to get your answer correct here. So hope that's clear. That I know that answer looks a little different. It is using some trig identities. I promise you, you won't get punished. You won't get penalized in any way if you don't know the trig identities. The computer will still accept the answer without the trig identity there. So, little explanation on why that looks the way it looks. Let's check out the next one. So now we got a car being towed up a ramp. So here's our ramp at, what are they calling the angle? Alpha. And here's the car, it's just a box, no reason to get too creative. Here's the tension going up. And I like to draw free body diagrams. Just, I think the math is a little bit cleaner looking that way. So here's the tension going up. Since it has mass, there's the weight, the force of gravity, and the normal force from the surface. And since the car is being pulled up, I'm going to use a coordinate system that's angled like this. So I'm going to use a coordinate system that's angled like this. And we got to be a little bit careful now where we put the sign of the ramp. So let me say this. This again has to do with some trig on how you get alpha onto your XY coordinate system. But let me just say this. The sign of the ramp, so the angle for the ramp, will always be connected to the weight. It's just a matter of whether you put it on the left or the right. So I'm either going to put alpha here or alpha here. But try to remember it's always connected with the weight. And when the ramp closes, so you gotta have to picture this in your brain. When the ramp closes, the angle is going to 0. So if I close the ramp, the angle goes to 0. Now I want to look at my free body diagram. If I close the ramp, that means the normal force starts to align with the weight. So if I close the ramp, it'll start looking like this. And this is the angle right here that is going to 0. So again, if I close the ramp, the angle goes to 0. If I close the ramp in this picture, which means the normal force is going to go straight up. Well, if I do that, it's this angle here that goes to 0. That is the angle of the ramp, and that's the angle we're going to need to sum our forces. So looking in the x direction, calling positive x up the ramp. So that means tension is just right along the ramp. We don't need any angle for tension because it's going right up the ramp. And the other component in the x direction is right here. And I'm going to try to draw this a little bit bigger. Maybe it should be, but there it is. Here is the other component in the x direction. So we have tension going this way in the positive x direction. And then we have the weight component pulling it back this way. This component is the opposite leg of the triangle, right triangle. Opposite leg means we're going to be using sine there. And so we have mg then sine alpha for this component here. Again, that's the opposite leg. And it's, whoops, oh man, I wrote that in the y direction. Let me rewrite that. It's in the, so that component again is mg sine alpha. It's pointed in a negative direction now. So negative x, positive x. There we go. Here's positive, here's negative. And Newton says this equals ma, but all these homeworks are in equilibrium, which means a is 0 there. And so we get that tension equals mg sine alpha is what we get there. And they want, so they're saying in the question here, when I actually look at the question, they want the tension to equal 1/3 of the car's weight. So here we go. Here's the tension I solved from doing the free body diagram, this thing up here. I got this equation. Now they're telling us this. So we can equate these because they both equal tension. And so we'll get 1/3 mg equals mg sine alpha. Mg's will cancel. And so we're looking for the angle such that sine of that angle is 1/3. And that's going to be then the inverse sine. Make sure your calculator is in degrees. So I'm going to do that right now. Make sure because I know I'm in radians. So let me switch that to degrees. I'm in degrees. And let me do arc sine 1/3 is 19.5 degrees. So I'm just going to round to 1 decimal place there. And that's my answer for that. And there we go. They didn't say anything about that at all. Usually, you know, sometimes they have a little blurb about something, but there is the answer. I just want to say for this particular problem, notice we didn't need to sum the forces in the y direction at all. So I was going to sum the forces in the y direction, but it turns out we didn't even need to solve this problem. So we just needed the x components, so these two pieces there, because that, let me just say it again, these two arrows are the sum of the forces in the x direction. We got this result from doing that, and then the homework told us this requirement, and then we just equated those two together and then solved for alpha to get that answer. So check out the next one. The adventurous archaeologist, who for certain isn't Indiana Jones, even though he's got the hat with the little Indiana Jones bag and everything. So we have an angle, find the tension in the rope. All right, so we got our dude hanging here. He's a rectangular box because that's what's easy to draw. And they're telling us the angle is this right here. They're telling us these angles are equal, so that's nice. It makes the math a little bit easier. And that's the picture. The free body diagram is meant to help you with the math part. So now we're going to look at the four forces, see which one's on here. So one, there's mass. So for certain, we have a force of gravity going down. We have two ropes. So, and because he's exactly in the middle, the angles are the same, does all imply that these tensions are exactly the same. So I'm just going to use the same T for both of these. And the angle that's here, we need to get onto our picture. So let me do this, maybe with a red pen here. Let me just make a rectangle right there. There's a rectangle. This angle is this angle. So that's just from trig. And that means then that it's right here, the angle. So that's where the angle is. And we'll sum our forces in the x direction. So in the x direction, we have this component to the left, and we have this component to the right. Both the adjacent leg of the tension, adjacent leg will be, we get from cosine. So just to say it again, cosine is going to be the adjacent leg, which is the x component we're looking for, divided by the hypotenuse. So we can solve for tx by just multiplying both sides by t. We have this one to the left. We have this one to the right. And you can see these are exactly equal, and that's going to equal 0. And I just want to state this again. Newton says when you sum the forces, this equals ma. But because the person's not moving, means acceleration is 0, and the whole equation then equals 0. So that's how I'm getting the equal 0 there, is because he's just hanging here. There's no acceleration. And so we get this result, which is pretty meaningless. It just tells us these two equal. So let's go to the sum of the forces in the y direction. Now in the y direction, we have these components up. We have this component up over here. We have this component up over here. And then we have weight going down. So those are the three components we're looking at. So let's look at the opposite leg. Opposite we'll get from sine. So that'll be a sine there. And that one's going up. This one's also going up, so we got another one of those. And then we have weight going down. Again, the person's not moving. Newton says this equals ma, but the acceleration is 0 here, so that whole equation equals 0. And we're looking for the tension. And the tension we can get then from this last equation, because these are like terms, so we can add these together. This minus mg, I'll just throw to the right side, make it positive. And then we'll solve for tension. Tension is mg divided by 2 sine theta. And do they tell us the mass? They do. They say the hero's mass is 85. So I have 85, 9.8, 2 sine, and the angle here is 11 degrees. And that's what I'll punch into my calculator. Times 9.8 divided by 2 sine 11 degrees. And I get 2183. So I'm just going to round to the ones place there. 2183. Let's see what they think about that. And they're good. They say my answer is rounded. Well, my answer is rounded to 4 digits correctly, but that's a sig figs thing. There's only 3 sig figs, so they only rounded to the 3rd digit. Again, no penalty for that. Just to be clear, you can see I'm getting the answers correct. No penalty for significant digits there. Part B, what is the smallest angle that the rope can have for it not to break? So we're going to need to know what the tension of the rope is. And it does say up here the rope will break if the tension exceeds. So what do we have? 2.5 times 10 to the 4. So that's 1, 2, 3, 4 newtons. So there's 2.5 times 10 to the 4th. That is the maximum tension that the rope can withstand. So going back to this result right here, because here's our relationship for tension. Well, we had to solve for tension before, given the angle. Now we're given tension, being asked to solve for the angle. So now we're saying tension is 25,000. This equals the mass of the person, which is 85, times g, which is 9.8, and then over 2 sine of the angle they want us to figure out. So now they want us to figure out this angle, and let me just write that in a new piece of paper. So we've got 25,000, 85, 9.8 over 2 sine theta. We're solving for theta, so I'm just going to move the theta up here, multiply both sides by theta, and then divide by the 2500. So we'll get this result, or cross multiplication there, whatever you want to call that. So there's our result for sine. We do have to take the inverse sine of this, so ultimately our answer is inverse sine of all this stuff. And that's what I'm going to type into my calculator, the inverse sine of that. Whoops, I hit divide. and divide by 225. Whoops, I put one too many zeros in there. That should be 25,000. And I get that theta is about 1 degree. It says 0.95. 0.95. I'm just going to type in 1. Let's see what it says. So just to be clear, my calculator does say 0.95. But let me just round that to 1 and just see what happens. So I guess that was too much rounding. Too much rounding. So there we go, 0.95. So so there can be too much rounding. So there you go. There is our answer, and here is the work for that. And something else I just want to say to you that, notice that now I am trying to write pretty big so you can read it, but this problem did take me about 2 pages. I am writing pretty big, but just so you know for yourself, I started with a picture, free body diagram, summing the forces, and then doing the math of putting it together. So don't be afraid, if you're taking 2 pages, that means something's wrong. You can see that I pretty much am using at least 1 page for all of these problems. So we'll check out the next one. And this picture is a little bit unfortunate because this dotted line here is meant to be horizontal, and I can they're saying the angles here are the same. A dotted line here is meant to be horizontal, and that might mess with your brain a little bit by looking at that picture. So I've never been in one of these things, but we do have actually technically a few free body diagrams here that I just want to kind of draw out here. So looking at the very top peg, so this top peg right here, we do have something connected to the wall on that top peg, and then there's a rope coming down this way. If we look at where the person's foot is, well, here we have the tension going up to that peg. We also have that rope pulling down to this peg, and the person's leg is pulling that way. And then on the bottom one where the weight is connected right here, we have the tension going this way, and then here is finally the weight of that block sitting right there. And they actually want us to focus on this one right here. It's really the one they want us to focus on. And if we look at that and sum the forces in the X and Y direction there, and we do have an angle of 35 degrees. So let me make this picture a little bit bigger. We have this, and this. This angle here is 35 degrees. Whoops, I guess you can see that. So here's X, here's Y. Here's just a bigger picture, zoom it in there so I can just write the math a little clearly there. So summing the forces in our X direction, and we have these 2 components to the right. So each one of these has the same component to the right here. So we're going to actually have 2 of these, one from the top, one from the bottom. So let me just right off the bat, it's also in a positive X direction. So let me just say we've got 2 of these red arrows. Again, this component is from the top. This component is also of this bottom one. It is the adjacent leg. So adjacent we'll get from cosine there. And the tension being the magnitude there, that's overall in the rope. Let's call that tension T. We want the X component. It's the adjacent leg. So that'll be cosine of the angle. And we do have 2 of these, again, because from the rope from the top and the rope from the bottom. And a person's leg is pulling to the left. So I'll just say force a person's leg. And it's meant to be traction. So Newton says this equals ma, but a equals 0 because the person's not moving. And so we're going to set that to 0 because we don't want the person's leg to move. That's the whole point of the traction system. I'm guessing. I've never been in one, but they're asking us to solve then what must the weight be what must the weight be? So we don't have weight in this equation at all. So we're going to have to go to the y, some of the y's to get the weight component in there. And here is the, I have to say this. The weight component is actually going to come from this piece right here, the weight component. So if we look at this free body diagram, I'm going to blow that one up a little bit more. Tension like that, mass of gravity down. I do have to say this. These pegs are probably bolted into the wall. And because they're bolted into the wall does mean there's also a force from the wall. Because if we look at this free body diagram right here, we can see tension has a component to the left. And if there was nothing to balance that out, then the pole would move to the left. So there is actually a force here from the wall that's connected to the peg. Same with this peg up here at the very top. You can see how the tension pulls it to the left. There is a force from the wall because the peg is nailed into the wall here. So there is a force from the wall here. We don't need that, but just in case you're curious what cancels out that X component there is a force from the wall and the peg. But we're just interested in the Y component here, that angle 35 degrees. So if we sum the forces up and down in the Y direction, we've got this tension. The up component right here, that's the opposite leg. So the opposite leg will be sine. And then that's being counteracted by gravity. And the leg's not moving, so the acceleration there equals 0. And we can get then that tension sine 35 equals mg. And then we can solve for tension. And the reason we're going to want that is so we can stick it way back up into there. So that's what I'm going to do. So we'll have 2 tension, which is mg sine 35. And then this is cosine 35 equals the force on the leg. And they're telling us they want the force on the leg to be 28. So that's what they're telling us. So again, I plugged this in to the top equation right here for t. Plugged it in for t. That's what this is down here. And that equals the force of the leg. And then they're telling us right here that the force on the leg has to be 28 newtons. So let me get another piece of paper for that. Let's see it all. So this is what we have. We got 2mg and cosine divided by sine is cotangent, and that's 35 degrees, has to equal 28. Now weight is mg, so because they are asking us to solve for weight and not mass, so they're actually asking us to solve for mg here. So this is really 2 weight cotangent 35, and solving for w then, we'll get 28 over 2 cotangent 35 for our weight. And let me see. So that is about 9.8. Really? The acceleration due to gravity. So the mass there is 1. All right. What if I just round that to 10? If I just round that to 10, I guess that's too much rounding. All right. And we'll go with 9.8. All right. All right. So I had to do a little thinking on that, and I did a little test run. There was something I was a little fearful about with this problem, and it goes back to this initial picture here, that there is a force from the wall that holds the peg in place. These pegs aren't just magically stuck in the wall with no force holding on them. And in order to get 17 newtons, is they assumed that this tension force, all of it comes from the weight. So Let me just show you that on a different piece of paper here. So I did this for the peg because the peg has a tension and there's a weight going down. The peg is clearly not moving to the left because there's a force from the wall on the peg. And so I included an angle there, and I ended up getting, what did I end up getting? I had a cotangent. Here it is. No, I had this result. This one. I had weight equals 28 over 2 cotangent 35. So that's what I had there. And if we ignore this force from the wall and we just say that the tension is all equal to mg, so that T just equals mg, well, that's not what I had. I had T equals sine. So I had a sine in there because of the angle and because of the force. But if we change this to T equals mg, so going back to this result here, where I had 2T cosine 35 equals the force in the leg, I had T is mg sine 35. That's what I had because of the force from the wall. However, if we say T just equals mg and ignore the force of the wall, then remember mg is ultimately weight here. We'll get 2 weight cosine 35 equals FL, which is 28. And then when we solve for weight, we'll get 28 divided by 2 cosine 35. And that is the 17 newtons there. Sorry if you can't see that. That's how they get the 17 newtons. So this is the correct answer, I would argue, because I'm including the force from the wall. This is the answer without including the force from the wall. So notice the only difference is the trig function here, cotangent versus the cosine. But that's how they get the 17. Now that I've done that problem, I'm not a fan of it. I'm not a fan. That might just be more complicated for you, the student, because you know these pegs are held into the wall. And this is something I try to say with introductory physics that can be challenging. That was my worry with this problem. Will they ignore the force from the wall or not? And it turned out they did. And as a student, how are you supposed to know that? Because I don't see how you're supposed to know that at all. So, this would have been a good problem if they just would have included the weight correctly there. But there it is. I won't have that one on test just because of that kind of change that they made there. But there is that one. 2 blocks and a ramp. Always a good question. 2 blocks on a ramp. And getting the force, the tension between those ropes. So let's see what we got. In terms of weight and the angle of the incline, calculate the tension in a rope connecting the blocks. All right. So here is our ramp. And what are they calling the angle here? They're calling it alpha. We have a block here. Same mass, and it's connected to a wall. Let me call this tension 1, tension 2. I'm just going to call these M. They're both the same mass. The problem says they're both the same weight. And since G is the same, that means they have the same mass. And let me do the 2 free body diagrams for both of these at the same time so you can see them. Starting from the left, we have gravity down. We also have gravity down on the other block. Both of these are in contact with the surface, so there's a normal force off at an angle since we have a ramp. And now here's where they're going to differ, is that this one has a tension up that I'm calling tension 2, and this one has a tension up I'm calling tension 1, but this block also has a tension 2 going down the ramp. So here's the block on the left, connected by 1 rope. Here's the block on the right, connected to the rope to the wall, as well as connected to the rope back to the other block. So we have an angled coordinate system here, and let's choose positive x to be up the ramp. So I'm going to choose positive x to be like this, up the ramp. And let's sum the forces in the x direction on this first block to the left. So positive T2 going in a positive x direction. And now our angled coordinate system is going to be our angle alpha of the ramp is going to go right here. That's where that alpha goes. Same with this other picture. Alpha will go right there. And the x component for this is pointed to the left. That's the opposite leg. I'm sorry. No, that is the opposite leg. That's the opposite leg. What gets us the opposite leg is sine. And so this is going to the left, which means negative mg, and then sine is what will get us that angle. Those are the two x components. We got the tension going up, and we got this weight component going down. That takes care of the forces in the x direction. The box isn't moving, so we can equate that to 0. If we sum the forces in the y direction, we have the normal force going up, and the other weight component, the adjacent leg going down. Adjacent is cosine. Again, the block's not moving up or down in a ramp, and so we know that equals 0. These are the sum of the forces for the left block. Now if we look at the right block, summing the forces in the x direction, we've got tension 1 going up, we've got tension 2 going down, and we also have this weight component going down. So negative direction, that's the opposite. So sine will get us the opposite. Again, the block 1 isn't moving, so we can equate that to 0. And then some of the forces in the y direction for this block, normal force going up, the weight component going down, that component, the adjacent leg, is cosine. Again, it's not moving up or down the block, so that equals 0. So here's some of the forces for block on the left. Here's the one for the block on the right. Our 4 equations then we got there from summing the forces. And let's see what they want. They want tension. They're calling it TAB. That's what I called actually tension 2, because I just think tension 2 is better than tension AB. So I am solving for tension 2. And tension 2 I can actually get from this equation right here. So right here, I can get tension 2. There it is. Tension 2, I'll just move this to the right side. So tension 2 is mg sine alpha. So there it is, tension 2 mg sine alpha. They want it in terms of weight and alpha, so there it is, mg is weight. Weight sine alpha is the answer. And, well, there's my answer. I'm just going to have them show it to me. And there it is, W sine alpha for our answer there. If we look at part B, in terms of weight and the angle, calculate the tension in a rope that connects block A to the wall. So now they're looking for tension 1. They're asking for tension 1, the one that connects to the wall. So I'm just going to look at my math. Well, there's no tension 1 here, so that's no good. No tension 1 here, so that's no good. There is a tension 1 here, but none here. So the only equation that I can use is this third one. It's the only one that has tension 1 in it. And so I'll just solve it for tension 1 by moving everything to the right side. So there it is. But we know tension 2 from the previous problem. It's right here. So I'm just going to plug that in. Tension 2. Now they do want to use weight. They do want to use W for weight for mg. So T2 is weight sine alpha plus mg here is also weight. And there's another sine alpha here actually. So these are like terms, and we could add these together to get 2 weight sine alpha. And so that's the answer for part B, 2W sine alpha. And I'm just going to request the answer to see it. And there it is, 2W sine alpha. So we calculated the tension between the blocks and the tension coming off from the wall. Part C says, calculate the normal force, all right? Well, if I look at my work, the normal force is right here in the y direction. Notice both of these are the same. Both of these are the same for both blocks. And so that's our answer right here. The normal force is mg cosine. So there's the answer for the normal force, all in our work. So just say this again, you know, I wrote these 4 equations down, and now I'm just looking at them to get my answers, and I'm finding the answers then in each of these various equations. So there's the third one, part C. Mg cosine alpha is what they're looking for there. And there we go. Remember again, where did I write that? Right here, I know it's getting a little sloppy. I wrote mg cosine alpha. Remember, mg is weight, so it is w cosine alpha, which is what they have there, w cosine alpha. And multiple choice, I'll let you take a look at. And these last 2 are multiple choice, just asking you about what happens if alpha is 0 or 90. And that just means plugging in alpha into this. So for instance, right here for tension 2. Tension 2 is W sine alpha. Well, if alpha goes to 0, well, sine 0 of 0, which means there will be no tension in 2. So if the ramp, so they're saying if alpha goes to 0, well, that means the ramp is now a flat surface, and well, now there's no tension in there because the block's not being held up by a ramp anymore. So that's what they're asking in the last 2 parts, just some multiple choice, and just asking what happens there. And just to be clear, in case you don't know, sine of 0, sine function looks like this, 0 at 0. Sine of 90 is 1. Well, that's the top point right there. So some angles we want to know, since they're asking about 0 degrees and 90 degrees. Let's check out the last one. And we got, what a giant safe. Oh, it's a loudspeaker. All right. And they want us to know the tension in the cables. So by them telling us the angles are the same here, means these tensions are the same, so it's perfectly in the middle. The angles are the same. They're saying that these are length L, which are telling us is 2.9 meters up top here. So here's what I'd do. Well, they already have a picture for us, so I don't know how good drawing a picture is actually once they already have a picture for us, but I'm pretty used to doing it. But the free body diagram is what is important here, I think. So the weight of the force of gravity, weight going down. We have these 2 tensions then supporting it. So this is just like the chandelier problem we started with, actually. Very similar to this. We do need to get these angles in. So let me just draw this again. This right triangle makes a rectangle. That angle here is that angle there. So that's trig stuff, which means this is where the angle is on our free body diagram. And I'm going to sum the forces in the x direction. So the x direction means this force is positive, this one is negative, and they're both the adjacent leg. So adjacent means cosine. So this one here is minus t cosine theta. This is positive t cosine theta. The loudspeaker's not moving, so this equals 0. We get this trivial math statement here that we'll be able to do nothing with, because trivial statements usually you can't do anything with, and so that's going to be pretty useless. Let's check out the sum of the forces in the y direction now. So here's a y direction. We got this going up, we got this going up, and we got this going down. So this component is the opposite leg. That means sine. So we do have 2 of them. We have this component here plus this component over here. And we have weight going down. And it's not moving, so that'll equal 0. These 2 are like terms, so we can add them together. And the minus mg, I'll just move to the right, make it positive. because we're trying to solve for tension. So I'm just going to solve for tension. Tension is mg over 2 sine theta. And let's see what information they give us. They do give us the mass. So we know the mass, g is 9.8. And the angle is what we need to figure out. Now the angle, they're giving us to it in a kind of Pythagorean way here. So they're telling us the height here is 2. They're telling us the hypotenuse is 2.9. And so from this information, we can get the angle. So we have the opposite. So sine is opposite over hypotenuse. So that's going to be 2 over 2.9. And then inverse sine of 2 over 2.9 will be this angle. And let me figure out what that is. So inverse sine of 2 divided by 2.9 is about 43.6 degrees. And so there is my angle then I have. So I have the mass, looking at the problem, the mass is 24, g is 9.8, all over 2 sine 43.6. So that's what I will also type into my calculator to get the final answer. So 24 times 9.8 divided by 2 sine, whoops, not inverse sine, regular sine. There we go. And I get T is 170.5. All right. What if I just call that 171? What if I just call that 171? What do you think about that, Pearson? And they'll take it. All right, there you go. So, you know, I have 170.5 is the better rounded answer, but 171 to 3 sig figs. Again, you don't get any penalty for sig figs, so don't worry about it. If you would have put 170.5, I'm sure it would have also accepted it. So there is the homework. This one does take a little bit more time. That's why there's fewer questions on it, because, you know, I just want to say it again. This is, now, again, I know I'm writing bigger so you can all see it, but, you know, this problem took me an entire page. And even by then, I'm still starting to lose some paper. So just try to have that mindset that, you know, you may not be able to solve these in 1 or 2 minutes. Just take your time, write it out, and let me know if you have any questions. I'll see you Tuesday.